If you've spent any time at all trying to use a modern AI, you've felt this. I mean, whether you're a developer or just, curious.
Oh, absolutely.
You ask it for something complex, maybe a bit of code or some technical chemistry, and you just get this wall of text about responsible AI.
Right, or a flat-out refusal. And the feeling across the community is always the same. People say the models feel lazy or nerfed, even lobotomized.
Yeah, lobotomized. That's the one I hear all the time.
And, the thinking is that safety and utility are this zero-sum game. The minute you add safety, you have to pay this, tax. That just makes the model dumber.
And it is frustrating. You know the raw power's in there somewhere.
Yeah.
But if you peel it back, you realize why they're using such a brute force approach. The risk they're managing isn't just hypothetical.
No, not at all. It's not about stopping the model from saying something rude. We are talking about genuine dual-use capabilities.
What do you mean by dual use exactly?
I mean, the kind of knowledge that could be used to create sophisticated software exploits, or even more worrying, to help with CBRN threats.
Chemical, biological, radiological, nuclear.
Exactly. That is the engineering reality these companies are grappling with.
So, okay, the risk is massive.
Yeah.
But the main tool we've had to fight it, this thing called data filtering, is it's shockingly crude.
It is. The paper we looked at has this analogy that just sticks with you. It says data filtering is like burning down an entire library because one book has a recipe for a pike bomb.
Wow. Okay, so to get rid of that tiny bit of dangerous information, you're just scrubbing huge amounts of training data.
You are. And not just the bad stuff, but all the adjacent, useful science, chemistry, physics, medicine, it all goes out the window.
And that's why the model suddenly acts dumb when you ask about organic chemistry. It can't tell the difference between a dangerous recipe and, say, the science needed for drug discovery.
It just nukes the whole topic to be safe. We've been stuck. We desperately need a scalpel, not a sledgehammer.
And that is the perfect segue to what we're looking at today, this new technique called Selective Gradient Masking, or SGTM. The researchers call it neurosurgery for large language models.
And that's not an exaggeration. It's a fundamental shift in thinking.
Okay, so let's get into it. How does this neurosurgery actually work? Because the problem itself sounds almost unsolvable. We know information in an LLM is, holographic, right? It's smeared across billions of connections.
It is.
So how do you surgically remove one piece of knowledge without just wrecking the whole thing? Where do you even make the cut?
Well, that's the clever part. You don't try to cut it out after it's learned. You change how it learns in the first place, during the training itself.
Okay.
The technique is called gradient routing. And what they do is they explicitly split the model's parameters into two separate groups from the very beginning. Think of it like creating two different pathways in the model's brain.
So you're pre-labeling the circuitry. What are these two pathways?
You have the retain parameters. These are for everything you want to keep. General knowledge, reasoning, all the safe and useful stuff. That's the core intelligence.
And the other one?
The other one is the forget parameters. And you can think of those as designated holding cells. It's a temporary quarantine zone specifically for harmful information.
I see the setup, but how do you actually enforce that? I mean, training is this chaotic process with trillions of data points. How do you make sure the bad stuff only goes into the forget bucket?
That's where the masking part comes in. It's a mathematical intervention. Yeah. When the model sees data that's been labeled as harmful, like a specific bioweapon schematic,
right,
the learning instructions, the gradients, are intercepted, and the system forces that update to flow only into the forget parameters.
So the normal brain, the retained parameters, are just frozen for that one learning step. They don't see it.
They're completely firewalled off from it. The dangerous knowledge gets physically segregated into specific little clusters of weights, and then once the training is done, you zero them out.
You just switch them off.
You ablate them. The knowledge is structurally gone, but the general intelligence is totally intact.
Okay, that's a huge step. But here's where I get a little skeptical. Data labeling is a nightmare. You can't possibly label every single toxic thing on the internet. You're going to miss stuff. Doesn't the whole system break if your labels are messy?
That's where this gets really cool. The researchers found that the model developed something they call the absorption effect.
The absorption effect. Oh, okay, what's that? It sounds like the model is cleaning up its own mess.
It basically is. After a while, the model learns a meta rule. It learns, toxic-looking stuff, patterns that smell dangerous, they go into the orange wires. It internalizes the routing system.
Great, so even if I show it a piece of unlabeled toxic data, it will recognize the pattern and automatically route it to the forget parameters on its own.
Exactly. It learns to self-segment, which means the whole safety system works even if the initial labeling is incomplete, which, let's be honest, it always will be.
Wow, okay, that self-routing is a pretty big deal. So let's compare this directly. How does this neurosurgery actually perform against the old sledgehammer of data filtering? Let's use that chemistry textbook example from the paper.
Right. So a normal technical textbook is maybe 95% pure, useful science, and 5% stuff that could be weaponized.
With the old filtering approach, you see that 5% risk, and you just have to throw out the entire book.
And the result is a safer model that is now terrible at chemistry, medicine, you name it.
But with SGTM, the model reads the whole book. It puts the dangerous 5% in that forget bucket and keeps the useful 95%. Then you just snip the wires to the bucket.
You get the safety without sacrificing the utility. And the numbers they got from their experiments really back this up.
Yeah, talk me through the numbers. How did they measure this?
They looked at safety, so how well the bad stuff was removed, versus utility, how much general knowledge was kept. And with the strict filter, the old way, the utility cost was just massive.
How massive?
To get a high safety score, they took a 67% hit to utility.
67%. So you're wiping out 2/3 of the model's competence in related fields.
You are. It basically proves that the lobotomized AI complaint isn't just a feeling, it's a mathematical reality of that method.
And with SGTM?
SGTM achieved the same high level of safety, but with only a 38% utility penalty.
So you're cutting the performance costs almost in half.
Yeah.
I mean, 38% is still a hit, but it's a much, much better trade-off.
It's a huge improvement. It shows we can get safety and keep a lot more of the model's brain intact.
Let's shift to the big security question then. Is this removal actually permanent? Because, a lot of LLM safety so far has been like a house of cards.
A thin refusal mask, yeah. The model knows the answer. It's just trained to say, I can't help with that.
Exactly. And we know bad actors can break those masks in minutes with a little bit of fine-tuning. Is SGTM just another mask?
No, and that's the key. This is the difference between asking a librarian to hide a book somewhere in the library and actually burning the pages of that book while leaving everything else on the shelves.
So it's destructive, not just superficial. How well did it hold up when they attacked it?
This was a crucial test. They put it up against another method, a state-of-the-art technique called RMU. RMU just collapsed. The dangerous knowledge was relearned, fully recovered, in just 50 fine-tuning steps.
50. So that's nothing. Anyone with a bit of compute could reverse that.
Trivial. But SGTM, it was a different story. It took 7 times more fine-tuning, about 350 steps, just to start seeing any recovery of the dangerous knowledge.
7 times more. And even then, it wasn't a full recovery.
Not even close. Which tells you the knowledge wasn't just hidden, it was structurally gone. To get it back, a bad actor would need a ton of compute, a lot of time, and crucially, a big data set of the exact harmful information they were trying to restore.
You're basically forcing them to reteach the model from scratch on that one topic.
You are. The barrier is just dramatically higher.
This leads right into what might be the biggest practical benefit for big companies. It seems like this could end the whole dual model problem.
The expensive dual model future, yes.
Right. Right now, if you want a super powerful model for your internal R&D and a separate safe one for the public, you have to train 2 completely different multi-million-dollar models.
It's a massive resource drain. But SGTM changes that. Because you separate the safe and dangerous knowledge in a single training run, you basically get 2 for the price of 1.
You train once, you deploy twice.
That's it. You get the full model, which is the retain and the forget parameters all switched on for your vetted internal researchers.
And then you get the safe model, where you just zero out those forget parameters for your public-facing apps.
It's transformative. It gives you incredible flexibility to manage risk without throwing away the core asset you spent months training.
Okay, it sounds almost too good to be true. We know there's always a catch. This hand of parametric knowledge, right? Stuff the model has memorized. What are the limitations?
The main one is what they call in-context attacks. SGTM is great at making the model forget, say, the recipe for a toxin.
It doesn't know the recipe anymore.
Right. But it doesn't remove its core reasoning ability. And that's stored in the good part, the retain parameters.
So if a user just pastes the entire dangerous recipe into the prompt, ingredients, steps, everything, the model could still use its general chemistry knowledge to help them.
Exactly. It might say, well, I don't know that specific protocol, but based on the principles of chemistry you've provided, you could make this more efficient by raising the temperature or something like that.
So it's not a silver bullet. You still need other defenses.
Absolutely. This is defense in depth. SGTM is the deep structural layer, but you still need your input filters and your output classifiers to catch what's happening live in the prompt.
And what about the other big caveat, the issue of scale? These experiments were on models up to, what, 254 million parameters?
That's right.
That's tiny compared to the 70 billion or 400 billion parameter models out there. How do we know this neat separation will even work at that scale?
It's a fair question, but the data on this is actually really promising. The researchers tracked what they called leakage, which is the bad information accidentally slipping into the safe parameters.
And what happened as the models got bigger?
The leakage went down, the routing mechanism got more precise and more disciplined with scale. It dropped from a rate of about 0.10 in the tiny 8 million parameter models to less than 0.01 at 64 million.
Which suggests this isn't some hack that breaks its scale. It's a real mechanism that gets better as the model gets smarter and has more capacity to specialize.
It strongly suggests that when you apply this to a true frontier model, you'll get an even cleaner, more effective separation of knowledge. It's a very positive sign.
So let's bring this all together. What does this really mean? It feels like we're watching a paradigm shift in how we do AI safety. We're moving away from refusal
The model pretending it doesn't know.
to genuine structural removal. The model actually doesn't know anymore.
And that distinction is just so important, especially for the whole open source AI debate. If you can prove that safety is baked into the weights themselves, that it's resistant to being fine-tuned away,
It makes the whole idea of releasing powerful open weight models a lot more defensible.
you're moving toward models that are safe by design, not just safe by instruction. It's finally getting that scalpel we've needed to solve the safety versus utility problem.
And that brings us back to that one limitation we talked about. SGTM is incredible at removing memorized facts, the what of a dangerous process.
But the core reasoning, the how, remains. And that reasoning can be applied to dangerous facts if a user provides them in the prompt.
Which leaves us with a really important final question for you to think about. If we get to a point where we can successfully remove all harmful memory from these systems, what are the inherent risks of pure, powerful, content-agnostic reasoning itself?